And welcome back. Now today we're going to be looking at a very small device, this little thing here. Now this is a 16-bit ADC with PGA. Sounds quite complex, doesn't it? What it actually means is it's an analog to digital converter with programmable gain amplifier, which means basically you can boost the signal coming in and sample it at 16 bits. Well, can you? Well, no, you can't really, because the way we're going to be doing it is that we're going to be using 4 inputs here. Well, we're going to use one of the 4 inputs as a single-ended device. That means, so we're treating them all as 4 individual inputs. What you can do, but which we won't be covering in this demo, is measuring the difference between 2 of these inputs. So, for example, if you had 5 volts on one pin, 3 volts on another, you can say what's the difference between the 2 and expect to get 2 volts. What we're actually going to be doing though is treating each one of these as an individual input. So I've connected a potentiometer up to this A0 input. There's the old pot connected straight into the Arduino. Nothing fancy going on there, but you might be thinking, why do we need an ADC when that Uno at the back there, or well actually a Nano, has already got 7 of them built in. The Uno's got 5. Why on earth would you want to have something like this? Well, there's 2 reasons. One, you might not be using an Uno, and if you're using an ESP8266, you've only got 1 analog input, probably not enough. This will provide you with another 4. Additionally, the resolution on an Uno is 10 bits, which means if you put 5 volts in there, you'll read a digital value of 1023. Okay, and as you turn the volts down from 5 to 0, so the 1023 will drop every 5 millivolts or thereabouts, 4.88 actually. As you turn it down, it will reduce that number. All well and good, and it works pretty well. You've got to admit it works pretty well, but 5 millivolts is quite a jump. Now, if you have, for example, instead of a potentiometer like this, if you had a temperature sensing device of some kind, and that was giving you, say, 1 millivolt per tenth of a degree, you might well want to measure that sort of very tiny change in voltage. Well, this isn't going to cut the mustard, is it? Because it'd have to change by 5 millivolts for you to get any change in that analog voltage noticed by the analog to digital converter. This one, however, because it has 16 bits of resolution, so 65,000 whatever it is, it will measure down to 0.187 millivolt changes. Now, straight away, I found out that the 16 bits includes a sine bit, and because you can't measure negative voltages, it means you've actually got half that resolution. So 32767 steps is what you can measure on a 15-bit input, which is effectively what we're using here, and the manufacturers state that quite clearly in their data sheet. Now, if we're going to use something like this to measure very, very small voltages, there is of course a danger that just touching it like this and getting close to it is enough to generate voltages on these wires. In fact, this is controlled by an I2C bus, which is running on here. That's running at 100 kHz, and that noise on here is probably enough to upset this if you're not very, very careful, and certainly me touching wires like this. Let's just fire up the simple sketch that I threw together. Now, we're not using a library, certainly not initially anyway, because I want you to see how pretty straightforward it is using this in this simple little mode. So let's fire up the sketch, see what we get. Right, here's a fairly simple sketch actually. It looks a lot more complicated than it is, because you have to tell the device what it is you want it to do down the I2C bus. Now, so the first thing we do, apart from declare the address, which is hex 48 by default, there are 4 addresses you can have on here, and they are determined by connecting the address line, which you can probably just about make out there. Let me get that a little bit closer. It is a tiny device. See the address line there? If you leave it as is, that is effectively connected to ground, and it gives you hex 48. But you can connect it, rather strangely, to SCL, SDA, that's the I2C bus lines, or VDD, and they'll give you a different address. Now, it's a bit unusual to connect anything to the I2C bus that isn't an I2C device, but that's the way this device actually works. It's clever enough to work out internally that no, you're not fiddling about with the I2C bus, you're actually telling me what address to use. Fine. Okay, now back to the code. So we've told it which address we're going to have it at. Now the first thing you do after you've initialized, if you like, the I2C comms bus, you must tell this to point to the configuration register. That is, configuration as is, I'm about to set you up and tell you exactly what I want you to do. In other words, I want you to use each of these 4 inputs as 4 individual inputs, not some kind of comparison between any of them. And I want you to take a number of samples per second from that input, and I want you to, I don't know, what else have we got here? Oh yes, what's the maximum voltage I'm expecting on that pin? One caveat at this point, probably worth mentioning straight away. Do not ever connect a voltage to the input pins here higher than the VDD voltage that you're using. Now this is quite a wide-ranging device. If I take a quick sneak peek at the data sheet, we see here that the voltage range, look, is between 2 and 5 volts. Now you might think, yippee, I can run that off 3.3 then, and you can, yes, but then you can only measure 3.3 on one of those input pins. Let's glue that back into place. There we are. Right, okay, so just bear that in mind. So I'm using 5 volts now, so I can measure up to 5 volts, which in itself is a little bit tricky because, well, we'll come on to that. Right, so back to the code window. Now, the way you tell it what you want to do is by sending 2 bytes down the I2C bus. Very simple. In I2C terms, or Arduino terms, you just do a write with the 2 bytes, 8 bits in other words, that you want to send down, and then you finish it with an end transmission, and that will tell it what you've expected it to do. And each one of these individual bits in that byte tells it something. So what we've got here, for example, bit 15, the very first bit you see here, bearing in mind that these 2 bytes are going to be strung together, so that's 15, and way down here is 0. So bit 15 is don't care. The next 3 bits from 14 to 12, I've got a 000, which means how to configure it, comparator or single-ended. Well, I want single-ended. Okay. The next 2 bits is the programmable gain. That is, what's the maximum voltage we're expecting on any one of these pins? And we're saying 6.144. But because we can only put 5 volts into VDD, you can never measure up to 6.144. You'll blow the thing up. So it's an odd design decision. Now you could set those last values to 0.01, which would make it 4.096 volts, but that's not the 5 volts, is it? So in Arduino terms, we sort of fall between 2 stools here. We can't quite get to the 6.144, and we certainly exceed 4.096. Now, of course, if your device is a 3.3 volt, then you're okay. Well, I say okay, it'll work, but once again, if you look at the next voltage down we can do, it's 2.048. So 3.3 falls again between those 2 values, but at least you can measure 3.3 very accurately, much more accurately than you could on the Uno. And finally, the bit 8, that's this one down here, it says, do you want to have a continuous conversion, or do you want to do it one time? Why would you want to do it one time? Well, this can go into a very, very low power sleep, 150 microamps. So it could be sleeping. You then fire it up via the config byte, exactly as we're doing now, and it will do that one-time conversion. Bang, done, finished, back to sleep again. So good for battery power. But we're not running on battery power here. We're just running on the standard 5 volt USB. Well, we'll be in a minute when I've plugged it in. So then, having set it all up and the thing is now running because you sent those through, you then say, right, the next thing I want you to do is actually point the I2C bus to the bit of memory inside here where the results get put, the actual reading of that voltage on here. So that's a simple wire write, and it's just all zeros, so that's very easy, isn't it? There's nothing to do with that. And then finally, we just say, I want to read 2 bytes back, please, from that memory location. Go and get them. Read them back. There's one read there. That's the most significant byte, the leftmost byte of a 2-byte integer. and here's the rightmost or least significant byte of that 2-byte integer. Put them all together and we have our value. Let's fire this up and see what we get out. And powered up we are. So what I'm expecting over here in this bit are some values. Possibly I need to tell it that we're connected. Right, let's connect this to COM port 8. There we are, we're connected, and right, okay, there we are, we're reading some values. Now, that's great, and if I move the potentiometer, to the left, it goes down, as you'd expect. We are delaying, incidentally, as you can see down here, 250 milliseconds between reads, otherwise this thing goes absolutely mad, you get thousands. So it goes down as you turn left, exactly as it would do with an Arduino. It doesn't go down to 0, look, funny. And then, of course, as you turn it all the way up to the other end, it'll go up to, well, close to 32,767. Now, if I just put it around about midway mark, take my hands away, if we then look at these values here, what's something you can notice? And it's obvious, isn't it? We have, well, not a steady value there. There is some noise, basically. It's not jitter because it's not time-based. This is just a varying value on basically what it's saying on this pin here. So, you might say, well, so what? We can just read it, do whatever we need to do. That's true. But if your Arduino is busy doing other things, as it probably will be in real life, you want to read a value from here, whether it's a temperature sensor or, well, anything, whatever it is you're reading, you want to read it and you want to read it accurately, and then you might want to read it again and say, has it changed? If it has changed, it might mean the temperature is going up or the temperature is going down or something, and I need to take an action, switch on a heater or turn on a fan, what have you. Well, if this keeps jittering about like this, well, it means your Arduino is going to be doing something that it doesn't need to do. Now, bearing in mind that these small differences in reading that we're having are down to the 0.187 millivolts change. So the 0.1875 millivolt difference in reading we're getting there applies to the 6.144. I'm not sure we're on 6.144. I think we might be on the 4096, but whatever. It makes very little difference. The point is we are getting different readings. Now, even by going near this thing, it will also change the readings. If you go near the wires or whatever, it dramatically alters it again, going down here near the pot. So the question remains at the moment is, what can you do about that? How can you get the readings to be a bit more stable? Now, I've tried a few things. If we go back up in the code window to the configuration here and here, for example, this bit here says how many samples a second do you want? Now, I've gone right down to 8 samples a second because I found it was a little bit more stable there. That's the first 3 bits on here, bits 7 to 5. It's those 3 bits. But you might want to put in 001 for 16 or 010 for 32 and so on. This is how many samples a second it's taken writing those values back to that bit of memory that we're reading from. But I found 8 was adequate. And, well, quite frankly, it didn't seem to make an awful lot of difference what I chose. This is the best I could get it. So going on to the Arduino forum, I just wanted to see whether other people were having issues with this. And they said, yes, we are. Now, it might be down to the USB power supply that I'm using here, but I've tried a number of things. I've tried this lead here. Let me just get it into shot. This lead here is a standard USB lead, but I've cut it at this point to remove the power so that I can power the board via another means. So I can read the data back from here, but not power it, and I can power something else in here. Well, I've tried powering it with this sort of battery pack, but of course that's got a buck boost circuit in there, hasn't it? So there might be a little bit of noise on there. And I'm thinking, well, even if we could power it by pure battery, perhaps 3 LiPos on here, that doesn't really help us, because if you're using this in a non-battery situation, you still want it to be accurate. So they suggested on the forum You could have a running average perhaps in your code. So rather than just reading it once, as we're doing here, we're saying read it and print it. You could have an average of, I don't know, 10 readings or something. I don't know. I've also tried, as you see here, I've tried shifting the output down and then back up again. What that is doing is saying, okay, we've got a 15-bit translator here, analog to digital converter. Let's make it a 12-bit, say, because whilst the analog version on the Arduino is only 10-bit, 12 might be enough on here, but that didn't really help too much. And finally I said, well, let's map the output in this line here, because the Arduino goes to 1023, but we could say, well, actually 5,000 is enough. 0 to 5,000 will be plenty. So let's see what difference that makes. What I'm going to do is uncomment this line, commentate the other line, and see if that becomes a little bit more stable. And what we're hoping for is a range of 0 to 5,000. And it's building and uploading as we speak. Be interesting to see what this value down here turns into. And more to the point, is it stable when we've done this? Because what we'd like is repeatability. That's the thing about electronics, isn't it? You want the same result to come out regardless. Right, so what's it doing? There's still a bit of noise there, isn't there? Look, it's 28, 31, 29, 28, 30, 31. So it's still noisy. Now if I change this, does it go down to 0 yet? Yeah, it goes down to 0. That's an improvement. If I turn it all the way out the other way, don't know what 10,000 is doing. Now I think there might be a loose wire. 4, 6, yeah. But it's still jittery or noisy. So that's a bit of a disappointment really, because I was hoping it would be a bit more stable than that. Now that's not to say the Arduino version is particularly much better in that sense. I've had noise on these analog pins on an Arduino Uno and Nano, but of course you need 5 millivolts to make some kind of difference on those pins, whereas here 0.187, that's not a lot, is it? As I say, it could just be noise, it could be random, it could be your PC next to it, or another piece of electronic device that's emitting some kind of field that could interfere with this. That said though, if you're prepared to ignore, hello, I've managed to break it, look. If you were prepared to ignore the jitter or the noise and remove the last, I don't know, 4 or 5 values out of that, so it becomes less sensitive but more stable, then it could still work for you. Right, I've got to fix this. Well, that's better. Right, pulling the wires off. So for example, if we said here 2208 plus or minus 5, is it the same? That would work. Be interesting to experiment a bit with that and just see how stable we could get it really in a real life situation rather than here on the workbench, as it were. Now let's have a look where I got this from in case you're interested in pursuing this a bit further. We'll go over to the browser window. Right, here's where I got it from. So I got it from AliExpress. It was only £1.32, it wasn't a lot really. And if we could crack that noise on that input, it would be quite good. So let me just change that code a little bit to see if we can get this £1.32 value for money. And here, that's the array. So we're having a 20 element array, so we can store 20 previous readings. There's a little count of readings. And in the main body of the program, what we're saying is take a reading as we would have done normally, fine, and then put that reading into one of the slots of the array. I'll come back to this in just a sec. So we take a reading, we put it into the array, then we say out of our 20 readings now, take an average. Now, what that's going to do, of course, is that for the first 20 readings, most of the array is going to be 0, so it will ramp up to value very quickly. Let me just draw that out so that you see what I mean. So basically, what we're trying to do is have a running average. Now let's downsize what we've actually got in real world, and we'll assume we've got just 5 entries. In fact, let me take myself off screen. There we are, that's better now, I can see what I'm doing. So there we are, so we have an array of 5 entries. Now to begin with, these are all going to contain 0 because we've initialized it to 0 when the program starts. But we take a reading in, and let's say it was 50, we put it into the very first array, so this is now can be 50, but these are all still 0. So if we would take an average, we say 50 plus 0 plus a little, that is still 50, and now we're going to divide by the number of elements in the array, so divided by 5, that equals 10. Now that's obviously wrong because we've only had one reading and we've ended up with 10. So the next reading comes in, let's assume it was 50 again. We now have a total of 100, and now we're going to divide by 5, and now we're going to get 20. And as you can probably see from this progression, eventually this moves towards what the running average will be, which is of course 50 in this case. So for the first n readings, however many elements we have in the array there, it will be wrong. So it might take a few seconds to actually get up to speed. But the beauty of it is, if we have another reading coming in and it was 51, rather than the immediate reading jumping from 50 to 51, we add all these up, and if we assume there was 50 in these, we'd now end up not with, as you might expect, 251 as some sort of strange reading. It's 251 divided by 5, and because we're working in integer mode, it's still only 50. So it's sort of ignored the fact this is a funny old reading. Now what happens then when we've done this 5 times? We've read 5 entries in, the last entry's gone in here. What do we do with the 6th entry? Well, the 6th entry says we've already done 5, we're going to reset the counter and start putting them in at the top again, so that the oldest reading will always get overwritten by a newer reading. So then we, whatever it was, say it came in here as 40, we'd read 40 and then the previous readings are 50, 51, 50, 50, and so it goes round in circles. So it doesn't use a lot of space up in your memory. We're only using 20 instances of an integer, which is 40 bytes for this little running total. Not a lot really, and I think we'll get some value out of that. Let's have another look how that works then. So back in our code then, we've taken these 20 readings and are now averaging them out over a period of time. Remember, we're still delaying a quarter second between a reading. So what I've got here coming out is the actual reading we've taken as the first value, and then the average reading as the second, just to show you how it smooths out those readings and gives a much more, a smoothed out reading, as I just said. So if I turn this, what's going to happen is, of course, that it's not going to be an instantaneous change. So as I move it down, you can see that the average is trying to follow what's coming in here, and it takes a few readings, look, before it gets down there. And that's not necessarily a bad thing. For example, would you want the speedo in your car to give you the absolute instance of that speed that you're doing at that precise moment? The answer is no. You want that speedo needle or your digits to sort of go up very smoothly and then back down again, fast enough so you get an accurate representation of your speed, but not so fast that it's going 30, 34, 33, 34, 33. It's got to be a nice smooth progression, and I think that's really one way of doing it like this. Now that's pretty good. Look, it still moves a little bit between a 4 and a 5, but that's better than what's happening here in this column, which is jumping about quite a way, isn't it? Anyway, that's I think that's added value now. And if we go back to our browser window, so £1.32 for this, not bad, very easy to program. As you saw in that sketch, you're not telling it that much. And if you want to change some of the parameters that I've put in, all you've got to do is change some of these bits here, and I've documented them out. So that's the first byte, bits 15 to 8. And these are the second byte, bits 7 to 0, and these are the bits you change within this and here. And most of these, in fact, I've got to be honest, won't do a lot if we're treating those 4 inputs as 4 separate inputs rather than in comparison mode, because a lot of this, look, is all talking about the comparison. Well, we're not using it like that. There is a data sheet that goes with this if you want to explore this a little bit more. So let me bring that one up. So this is the data sheet from Texas Instruments. Now, so it covers the family really. So you've got ADS1115, 4 and 5, but we're looking at the 5 because that's the most advanced one with the programmable amplifier. So you can say 6.144 volts or 4096 or whatever. Now the bit about the configuration register is a little bit further down, so let's zoom down there. Right, so it really starts from about here. This is the pointer register that we're talking about, how to point to either the configuration or the conversion or whatever. On the next page, it starts here actually, it tells you all those bits. These are the bits that we were talking about and what I've documented in that sketch. So you can control how many samples a second, whether you want comparison mode or for single-ended. There's a fair bit you can do here. If you get one of those other modules, most of these bits don't do anything anyway, so you might as well stick with the 1115 here and experiment a bit. Good, I think we've sort of covered this one, bit of a niche product, but as I say, if you've got an ESP8266 or well, even a Raspberry Pi that doesn't have an ADC as far as I'm aware, then this sort of thing could really make a change. And you don't have to have it as accurate as that, of course. We can decide that well, we don't need this level of accuracy showing here at the moment. You just want standard 10-bit, or do you? 1023. Well, you can do that here. You can either have a running average that divides by 10 or 100 or something. Whichever way around, though, it gives you that possibility. So there we are. I think we're done. Good value for money, £1.32 for something like this. And it uses I2C, so you can hang 4 of these on that one bus. Don't forget that. Good. Okay, I think we've covered it. Thanks for watching. If you've used this before and you've used it for a real world project, do let me know in the comments underneath. I'll put some links in under there as well for the data sheet and so forth. Great, thanks for watching. See you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.